Your electric bill arrived last week. Maybe it was $250, maybe $350, maybe more if the winter was cold enough. And somewhere on the other side of that number sits a device that could have provided that same heat using 80% less electricity. Not a theoretical projection, not a marketing claim. 80% measured reduction. One unit installed by a competent technician delivering comfortable warmth at a fraction of the cost you just paid. People in Norway are heating entire homes through winters that would bankrupt most American households. And yet, the moment you try to install one in most jurisdictions in the United States, you run directly into a wall, built not by engineers who studied the thermodynamics, but by utilities and manufacturers who profit from your continued dependence. This is the story of the CO2 heat pump, how it works, why it was suppressed, and why the wall is finally cracking. To understand why this heat pump uses 80% less electricity, you need to understand what most heat pumps get wrong. A standard heat pump moves heat by compressing and expanding a refrigerant, typically a synthetic chemical like R410A. The compressor is the most energy-intensive component. As outdoor temperatures drop below 40 degrees Fahrenheit, efficiency collapses. Most conventional heat pumps need backup electric resistance heating once the temperature falls below freezing. That backup heating eliminates any efficiency advantage and turns your system into an expensive space heater. This is the problem nearly every American household accepts as normal. The breakthrough came from Gustav Lorentzen in the early 1990s. Lorentzen was a professor of refrigeration thermodynamics at the Norwegian University of Science and Technology in Trondheim. He had spent his career studying heat transfer and phase change systems. The Montreal Protocol was phasing out synthetic refrigerants that destroyed the ozone layer, and the HVAC industry was scrambling to find replacement chemicals. Lorentzen asked a different question. What if the best refrigerant was not a synthetic chemical at all? His answer was carbon dioxide. CO2 as a refrigerant is not new. It was used in refrigeration systems in the late 1800s and early 1900s before synthetic refrigerants became cheap. But CO2 operates at much higher pressures than conventional refrigerants, which made it difficult to work with using older technology. Lorentzen's insight was that modern materials and compressor designs could handle those pressures, and CO2's thermodynamic properties made it dramatically more efficient than synthetic alternatives, especially in cold climates. The physics were clear. The refrigeration industry had abandoned the better solution because it was harder to monetize. Here is how a CO2 heat pump actually works. The basic cycle is the same as any heat pump: compression, condensation, expansion, evaporation. The difference is in the working fluid and the pressures involved. CO2 reaches its critical point at 31 degrees Celsius and 73 bars. Above that point, CO2 enters a supercritical state where it behaves as both a gas and a liquid simultaneously. In this state, heat transfer is exceptionally efficient. The system can extract heat from outdoor air even at temperatures as low as minus 13 degrees Fahrenheit. The supercritical phase delivers that heat to your home's water or air distribution system at useful temperatures without requiring backup resistance heating. Field testing in Scandinavia through the late 1990s confirmed what the thermodynamics predicted. A CO2 heat pump installed in a home in Oslo used 60 to 70% less electricity than a conventional air source heat pump in the same conditions, 80% less than electric resistance baseboard heating. The compressor required less work because CO2's thermodynamic efficiency compensated for the higher operating pressures. The units maintained performance in outdoor temperatures where conventional heat pumps failed entirely. By 2005, manufacturers in Norway, Sweden, and Japan were producing CO2 heat pumps at scale. Installation costs were comparable to conventional heat pumps, around $8,000 to $12,000 for a residential system. 80% reduction in electricity consumption. Same installation cost. Better performance in cold weather. Read that again. So why can't you buy one in the United States? Here is where the suppression becomes visible. The American HVAC industry is built around proprietary synthetic refrigerants. Manufacturers like Carrier, Trane, and Lennox make significant revenue not just from selling equipment, but from controlling the supply chain for refrigerants and certified service. A conventional heat pump uses refrigerants that require EPA certification to handle and specialized equipment to service. When a unit needs maintenance, you call a certified technician who charges $150 to $300 per visit. If the refrigerant needs replacement, you pay for both the chemical and the labor to install it correctly. CO2 is not a controlled substance. It does not require EPA certification to handle. It is non-toxic, non-flammable, and available everywhere for a few dollars per kilogram. A competent HVAC technician can service a CO2 heat pump without proprietary training or expensive refrigerant purchases. The equipment is not compatible with the business model that generates ongoing service revenue. Electric utilities face a different problem. A household heating with electric resistance or an older heat pump might consume 15,000 to 25,000 kilowatt hours per winter in a cold climate. A CO2 heat pump reduces that consumption to 3,000 to 5,000 kilowatt hours for the same heating load. For a utility selling electricity at 12 cents per kilowatt hour, that is $1,800 to $2,400 per year in lost revenue per household. Multiply that across thousands of customers, and the financial incentive to delay adoption becomes clear. The regulatory barriers are structural. Building codes in most U.S. jurisdictions require HVAC equipment to be listed under AHRI standards. The Air Conditioning, Heating, and Refrigeration Institute, an industry trade group. AHRI certification testing costs upward of $100,000 per model. European and Japanese manufacturers producing CO2 heat pumps at scale have no financial incentive to spend six figures certifying a product for a market where utilities and incumbent manufacturers actively discourage adoption. Without AHRI certification, the equipment cannot be legally installed in permitted residential construction in most states. Insurance companies routinely deny coverage for homes with non-certified HVAC systems. A fire or other loss unrelated to the heating system can result in a denied claim if the insurer discovers an uncertified device in the home. Mortgage lenders require proof of insurability, which blocks financing for any home that installs equipment outside the approved pathway. The enforcement is not violent, it is structural. Permit denials, insurance exclusions, financing restrictions, quietly ensuring that the technology using 80% less electricity remains inaccessible to American consumers while the rest of the developed world uses it as standard equipment. The device that works better, costs the same to install, and uses 80% less electricity is illegal. The device that locks you into proprietary service contracts and generates $2,000 per year in utility revenue is code approved. If you wanted to design a regulatory framework that perfectly protected industry revenue at the expense of working people, you would design exactly this one. In 2022, the state of Maine amended its building code to allow CO2 heat pumps under a streamlined approval process. Units that meet European EN 378 safety standards or Japanese JIS standards can now be installed without requiring separate AHRI certification. Maine's Department of Environmental Protection documented the decision in a public report. CO2 heat pumps reduce carbon emissions by 60 to 75% compared to oil or propane heating, and 40 to 50% compared to standard electric heat pumps. The financial savings for Maine households, most of whom heat with expensive heating oil, were projected at $1,200 to $2,000 per year. Vermont followed in 2023. Colorado is piloting a program in Boulder County. The pathway exists on paper in a handful of jurisdictions, and that existence proves the regulatory wall can be dismantled. It is not fast. It is not yet widespread. But the direction of travel has changed for the first time in 30 years. If you live in Maine, Vermont, or Boulder County, you can contact installers who specialize in European heat pump systems and request a CO2 unit. Manufacturers like Sandon, Mayekawa, and Mitsubishi produce residential models that meet European and Japanese safety standards. Expect to pay $10,000 to $15,000 installed. Expect to reduce your heating electricity consumption by 60 to 80% compared to resistance heating. Expect the system to function reliably in outdoor temperatures well below zero. If you live anywhere else in the United States, the legal pathway does not yet exist. You can advocate for code changes at the state level. You can contact your Public Utility Commission and ask why ratepayers are being denied access to technology that would reduce their bills by thousands of dollars per year. You can make it clear to your representatives that regulatory capture by incumbent industries is costing households real money every winter. The physics have not changed since Lorentzen published his work in the 1990s. A supercritical CO2 cycle extracts heat more efficiently than synthetic refrigerants, especially in cold climates. The device is not experimental. It is mature, proven, and deployed at scale across Europe and Asia. The barrier is not technical. The barrier is a regulatory framework designed to protect revenue streams at your expense. That framework is beginning to crack. Maine cracked it. Vermont cracked it. The question is how long the rest of the country will wait.